Well, thank you, and thanks all of you for being here, and thanks for the organizer to give me this opportunity and this honor to open this conference, which is on really a fascinating topic of correlations and quantum optics. And here, before starting, I would like to very much emphasize the work of Lorenzo Casiotto and Josephine Eckner, who is the two PhD students on that project. Now Josephine has graduated, and also let's say the material from Werner Beckscheider was really being also crucial in conducting those experiments. So obviously our attack on the problem is really trying to think, okay, what is the influence of vacuum fluctuations? And we know that vacuum fluctuations have consequences, measurable consequences in the world, and spontaneous emission. The most celebrated example is also the Lamb shift. And one thing which makes also this whole research interesting is that if you think about the Casimir effect, which is a very striking effect, because here you have a force that arises from vacuum fluctuation, and these vacuum fluctuations, in a sense, enter in the game only through a cavity. And this is also what long ago Edward Purcell already conceived, is the fact that you can modify the behavior of an atom, in that case the spontaneous emission, by using a cavity, enhancing or suppressing vacuum fluctuation. And the question is, of course, can we use and engineer those fluctuations in the context of solid-state matter, and can we have also, in that context, measurable quantities and measurable effects? So this whole topic has been really gaining a lot of momentum recently, and the question really in generalities, which is also referred sometimes as cavitronics, is can we make devices in which properties such as superconductivity, ferroelectricity, ferromagnetism can be engineered using cavities? And there's been mostly a lot of theoretical work, and of course the question is, can we observe things, and can we measure something? And our attack on it is really to take it on the side of transport, and the main question we would like to answer ourselves is, can electronic transport be modified by vacuum fluctuation? So very roughly, if I make a cavity and I can in this way modify the spectrum of vacuum fluctuation inside the cavity, can I change the way electrons move in the crystal due to those fluctuations? To start with, of course, it looks very bad, because in a way the energetics is against you. The ratio of the speed of light to the sound velocity is, if you put it to the cube, gives you a very small number, and so the contribution of vacuum fluctuation, pure electromagnetic fluctuations to the energy of electrons seems extremely small. But there's one thing which still is interesting, is that all those electrons, they basically talk to the same optical mode. So the scale, the fact that you have a large scale for the electromagnetic field, which of course makes it also very weak energetically, is also interesting, because it actually is a one-to-all coupling. So one thing, when you move from cavity QED in atomic system to kind of the equivalent of cavity QED in solid state, there are a number of things that change, and change in a way also that can make your effect stronger. Because if you think about atomic clouds, most of the time you can really think of the atom being extremely small compared to the wavelength of light, and therefore the dipole approximation really makes a lot of sense. The field is transverse, and typically also the cavities are larger than the wavelength. Now, if you look at the same type of problem in the context of solid state, and if you think in terms of low frequency cavities, so terahertz or mid-infrared or even microwave, there the cavity will be, for reasons I will detail a bit further, but most of the time can be described as an LC resonator, where you can actually put the electric field inside a small gap of the capacitor. As such, then the cavity is deeply sub-wavelength. You can enhance vacuum fluctuation this way. The field does not, because you are not a plane wave inside, it's not transverse, and because you can now excite collective states of electrons, this collective state might actually have a wavelength which becomes comparable to the spatial gradient of your electric field. So you might actually even lose the dipole approximation. And so we claim that the quantum Hall system is actually a very, very good system to study this type of physics. Because, of course, Lamb shift and Casimir effect are very small, but in the quantum Hall, you can couple the electrons very strongly to a cavity, because you can make very confined cavities, which are those LC resonators. The electrons have a low mass, so they have a large dipole, so the oscillator strength is actually 10 or 13 times more larger than what you would have for a free electron. And as such, you can observe this extremely strong light-matter coupling regime. You have a large dielectric constant, so the ratio of the interaction to AC field compared to the DC field, which is the pure Coulomb, is actually favorable in that sense, because you're reducing the Coulomb interaction and enhancing the dipole coupling. And you have a flat dispersion because of the magnetic field, and therefore interactions play a large role. So you basically cut the kinetic energy. So in addition, if you're looking at transport in the quantum Hall regime, you have this advantage that you know what you should be getting, because you should have a quantized transport. So you can really look at deviation from that quantized transport. And you can study both single particle and composite fermions systems. So just as a quick reminder, what we're considering are electrons in a very high mobility 2D gas. We put a magnetic field, you get Landau levels. And what we are looking at is optical transition between the last field Landau level and the first empty Landau level. And that transition, of course, has a frequency which is linearly dependent on the magnetic field, and is also, the whole oscillator strength is between those two adjacent levels. So each adjacent level has the whole oscillator strength of the transition. This, of course, grows also with an index of your state. So the transport experiments are the quantum Hall transport experiments. So we have a Hall bar, we inject a current, measure the voltage, either longitudinal and transverse. When the Fermi level is inside a Landau band, in that case, we do not have quantized transport, and you see basically transverse and longitudinal resistance. Longitudinal resistance is non-zero, but whenever your Fermi level is between Landau band and in the disordered band, then you can see the quantized resistance. We also should remember, and that's going to be quite important, is that we have electrons which are spin up or spin down, and under magnetic field, this degeneracy is lifted, and therefore you can also have a plateau when your Fermi level lies between two Zeeman splitted levels. Okay, so a few words about this cavity in which we now put our Hall bar. So you see we have this Hall bar, we inject current longitudinally, we can measure it transverse, and our cavity is basically a split, what people call a split ring resonator. An electrical engineer would say it's a slot antenna. Basically what you have is you have a capacitor, and the current flows around the capacitor through the metal. So you basically have a cutout on a high conductivity metal. And you can think of it as a LC resonator. And what you should remember is that in an LC resonator, the electric field is in the capacitor, the magnetic field is basically around the inductor. So here in that case, we can confine very strongly the electric field. The magnetic field is not so confined. And because of that, if you write now the light-matter coupling, the collective light-matter coupling of n particle to that electric field, you see they have this square root of n dependence, but you also have this vacuum field, and this vacuum field corresponds to the vacuum fluctuation inside the resonator, and that vacuum field inside the resonator grows like 1 over the square root of the effective volume, and because you can make this effective volume much smaller than lambda cube, you can actually get very relatively strong vacuum field. But what you can see already at the level of the field inside the resonator, this is a simply a finite element simulation of the resonator electric field a bit below the resonator, you see that not only do you have strong field, but you have also strong field gradients, meaning that you see here that the field changes at the edge. And then you can really think of it as almost an electrostatic problem, because the metal has such a high dielectric constant that, it's basically electrostatic. You have charges on each side, and then you have the field in between. It really works like a capacitor. So just a reminder, all those experiments I'm going to be showing are measured inside the Dill fridge. It's all closed, so there is no irradiation. It's 10 millikelvin, or when we do, of course, a temperature sweep, we go up above, but you can think of the electromagnetic field is in the ground state. That's the important thing. All right, so the initial experiment we did in quantum Hall was to compare the quantum Hall trace measured in a reference Hall bar to a quantum Hall trace measured in a Hall bar immersed into one of these cavities, and we saw very strong changes in the traces. Mostly, we lost the quantization, especially strongly in the odd filling factor. And I would just go a bit fast on that one because I want to come back from using the results of the newer experiment. And at that point, the explanation that was given to us suggested by Cristiano Ciuti was that what we have is we basically have scattering. So, of course, the quantum Hall is a topologically protected state, but if you have a scattering that can overcome this topological protection, then of course you lose this topological protection. And here, the idea is that we have a long range, medium range, if you want, interaction coming from electrons that basically do this anti-resonant process where they go up 1 lambda level and emit a photon, and immediately after, the photon is reabsorbed and the electron goes down. So you immediately have can show that you have a dependence of that process, like the square of the collective Rabi coupling, so omega r square, which is, of course, characteristic of anti-resonant terms. So now we really try to get a bit more intuition, or let's say, on what exactly is going on in these systems. We basically went to another experiment, which was not an on-off experiment. Here, the idea is that we separated, instead of having a resonator that is basically evaporated directly on the Hall bar, but we now looked at the resonator and the Hall bar separate inside the cryostat. And now what we could do is we would basically, inside the cryostat at low temperature, we simply move the resonator in the proximity of the Hall bar and move it back. And we did it in a way that we first touched once. We had what called landing pads to know where we were. We could check also that the resonator was parallel with the Hall bar, and then we retracted and we could do measurements. So for me, the take-home message here is that on one hand, because we now, of course, can change the light-matter coupling inside the 2D gas continuously from the maximum of something like 30% when we are something like 0.3 micron away from the Hall bar to basically no coupling when we are 1 to 0.2 millimeters away. That's, of course, the very nice thing. But there is no mechanical interaction between the resonator and the Hall bar. They really don't touch. And we also did many of those, a few of those up and downs, and we could check that whatever we measured was reversible. So effectively, those are the data. So we see here as function of different locations. Yeah. Oh, sorry.
So I guess I was told to interrupt. So
sure. Of course. Sorry.
So you had this plot on the previous slide.
Yeah.
Is this power law? What power?
That's a very good question. Honestly, this is the result of finite elements. I don't think it's a power. Yeah, it's probably a power law. It's probably also almost, again, electrostatics, more or less.
So these data points are measured or simulated?
No, those data points, we thought about doing the experiment, but it's a very tough one. We are sort of trying to make one now, because the difficulty is to make, what we do here, the way we evaluate the light-matter coupling is we do a finite element simulation. We plot the polaritons, and we infer the light-matter coupling from these polaritons. To do the experiment is extremely difficult because you would need to go through one single resonator and do that for samples that are spaced differently. So it's really, really difficult. So we basically based ourselves on the finite element simulation and the fact that we've done really we've done a lot of those optical experiments where we couple those resonators to 2D gas, and we could check that, those finite element simulations, they really work. So we can always explain, they contain really most of the physics that happens in terms of the optical response. Yeah.
Okay.
While we're already stopping,
sure.
So you just showed previously that the field is concentrated at the edges of the cavity, which, in order to change RXY, you would imagine you want it to be concentrated in the middle of the cavity. So I was wondering if you can maybe do the experiment with a movable cavity, but just rotate the cavity so that the field, the maximum of the field.
Let's say you see, the point is, what I showed you was the field of the empty cavity. Now, the field of the empty cavity is non-zero in the middle. So it basically has this shape, it's kind of flat and then grows at the edge. Maybe a factor 1, 2, 2, something like that. The tricky thing is, whenever you couple that cavity to the 2D gas, as I will show, I have some simulations afterwards, the field inside the 2D gas has a much stronger and much sharper change at the edge. And the reason is that the 2D gas is basically screening the AC field, and more or less, it's almost like, again, electrostatics, because we are at low frequencies, and so the field really is very strongly changing at the edges of the 2D gas. Now, concerning your question about moving the cavities, yes, we can move the cavity X, Y, and Z. So we cannot rotate it, but we can. And we had indications, so we used, in a sense, we realigned the cavity and basically maximizing the effect we were seeing. But we are blind. That's the problem. We don't have, because we cannot disturb, we cannot inject optical fields, we cannot apply high electric fields, because anything of that will disturb the 2D gas irreversibly. And that's why basically we have the only thing we can do is we can check the height, and we aligned it before cooling down, and we checked back afterwards that it has not moved. Yeah. No, okay. There's no, so, yeah, thanks for the questions, really. And so here what we saw is a clear change. The effect, as you see, is not as dramatic as what we saw when we actually had the cavity evaporated directly on top of the 2D gas, but still there is a measurable effect, and there's a measurable effect that really, there's a host of different things that happen on those traces, and what we're going to do is now walk in different magnetic field regions and look at what happens in different magnetic field regions. If you look at low fields, one thing which we observe here is a slight change in the Shibnikov-de Haas associations, which is something that we had observed. This was actually the initial observation we published in 2019. And here, the strongest effect is here. You see that those are all the odd filling factors are very strongly affected. If we now zoom in this region and we look as function of a distance between the resonators, so coupling, if we go from no coupling, where you see this plateau number 27 and 25 are actually nicely quantized, as we move the cavity closer and closer, we lose this quantization, and we get really a rather strong effect when we go 2.3 micron. You see that there is also an effect on the even plateau, but it's much weaker. And now our present interpretation is the even plateau is this cavity-assisted hopping, but the odd plateau is actually a different effect, and this is renormalization of the G factor. So how did we quantify this? Well, what we did is for every single distance to the resonator, so not all of them, but a few coupling strength, we did a temperature scan of the transport. And from this temperature scan, we can extrapolate an activation energy, and in this way get the transport gap, which we can actually do now for different distances, and also we can plot for the various different plateaus. And now what you see is something that makes a lot of sense. We have a linear dependence of that gap as function of magnetic field, and you can interpret this one as an effective G factor, which arises from the exchange energy. And what we do here is we change this exchange energy and change, therefore, the effective G factor. So this interpretation is that just a few words about the model that Cristiano Chiuti proposed for that, is the fact that we have not only field inside the cavity, but we also have field gradients. And that I come back to the question that was here. Here we have now a finite element simulation, not only of the resonator, but the resonator coupled to the 2D gas. And what you see is that there is actually a field has a maximum at the edge of the resonator and another very sharp maximum at the edge of the 2D gas. So if you zoom here, you see that we have very strong field gradients at the edge of the 2D gas, up to something like 210 to the 8 volt per meter square. Now, what should be also reminded is that in those quantized transports, we expect the current to be carried by edge states, and therefore having most of the action happening only at the edge where the gradient is very strong is actually fits together. So there's no contradiction there. So this is, this is a slide from Cristiano. So basically what he did is he did a Hamiltonian approach where he introduced this gradient of the field, and after manipulation could get an effective electron-electron interaction through the cavity, and this is all in this archive that you can consult. And effectively what he shows is that the electron-electron, this effective cavity-mediated interaction is attractive and therefore reduces the effect. Yeah? Yeah, sure.
Sorry, I heard from you that everything is electrostatic, and I fully understand that. But then, then for the theoretical explanation, this is a bit weird. Like, okay, there is this electrostatic mode, which is the cavity mode. But then, what about image charges? I mean, you put a lot of metal around your sample, and I guess this could not be a source of some effect.
Well, you see. Just to really clarify, and this is this question of electrostatics is really something where I would like to spend 1 minute just really meaning what is electrostatics and what is not. So when I meant electrostatics, I meant the electric field profile is very similar to the one you would solve for a DC field. Now one has to be careful that it is still at a finite and non-zero frequency. So the effect is really an AC field effect, such that because at zero frequency, there are other screening. We have two screening, the doping layers are actually have an excess electron density. So you have this very high mobility 2D gas in the center and two doping layers. Those doping layers have actually a finite resistivity such that they do screen DC fields. They are completely transparent to terahertz fields. So that's why, one has to be a bit careful about what we mean by electrostatics. So I think electrostatics is important to remember if you want to have an intuition on the field profile. This, I think, is perfect, and you just simply assume you have charges at the edge of your capacitor, and that gives you more or less the field profile. But let's say the effect on the electron is really an AC effect, so it's not a Coulomb, direct Coulomb. Now, you could say, well, am I dealing with some sort of a dynamical image charge screening? Yes. It would be another way of describing it, probably, I think. It's not been done to my knowledge, but I think at least I don't see any fundamental difference of thinking I have two electrons that interact via, but then you have to really remember that you need to have this resonator, which basically synchronizes the field over the whole length. That's the way, at least, I see it.
Thank you very much.
Okay. Okay, so basically, and so what we saw was that in this odd integer fraction, we see that essentially we lose the quantization due to the cavity. But what is really striking is when we move and we observe fractions, which are between the n equals 2 and n equals 1 plateau. So when you have basically between your Fermi level lies between the two Zeeman splitted levels, what we see is kind of surprising because we see an improvement of the plateau as we get stronger, as we get the stronger light matter coupling. Now, again, this is not a very large effect, but still you can see it here. For example, the plateau definitely widens and gets more well-defined in these various plots. And we also measured it using this activated transport. So we try to infer the activation temperature. And now what is striking is when we look at the 5/3, 7/5, and 4/3, which are all those plateau, all those fractional states which are between the n equals 2 and n equals 1, we see an improvement in the activation temperature. While if you take it a 4/5, which is slightly higher, which is within the n equals 1, so there are two differences between those three states and the 4/5. One is that it's between n equals 2 and n equals 1, and the other one is they are in the Jane sequence. Those three are derived from the 1/3, while this one is derived from the 1/5. So we don't really know why, let's say, we don't have really a firm theoretical explanation why that changes, but what I think is clear here is that we have this very striking effect that we improve the quantization, and we basically improve the quantization on some fractions, not others. Now, also one thing, just to make it clear, if you take a very large sample and measure what is the activation of the fraction on a very large sample of that same material, you get an even higher activation temperature. And the interpretation is, it's known in the fractional quantum hole community that if you want to have good fractional states, you should not make your hole bar narrow. And we, of course, because we want to fit inside the cavity, we need to make a narrow hole bar. So this is, so in a sense, you could say, well, what the cavity does, it helps against this disordered induced reduction, or we improve. We don't know whether we improve the maximum electron-electron gap, or whether we actually simply reduce the effect of disorder. So again, this, Cristiano did the same model that was used for explaining the G factor. If you combine with a Roton theory, you actually can also predict an improvement of the of this 1/3 fraction. So the last thing I would like to discuss experimentally is another collective effect, which is this formation of stripes. And this was observed experimentally many years ago, like 25 years ago, when people starting to have access to very high mobility 2D gas materials, and they observed that the transport could be extremely anisotropic in their samples. So here, for example, they were measuring a hole bar that was etched in one direction and the other direction, and they saw that between two plateaux, the Shibnik of the Haas resistance was extremely changed a lot for these half integer values of 9.5, 11.5, 13.5. So between plateaus. And depending, when we were doing that in square samples, they even observed extremely large ratios. But let's keep it to the whole bar measurement. And the understanding was that, well, it was shown theoretically that there is an instability of this quantum hole liquid, and that whole liquid will tend to form density to make stripes. And so charge density waves, and they would align, and here the idea was they aligned in one preferential crystallographic direction, and that was the reason this very strong anisotropy was observed. Now, we did the same experiment, and we here have two samples, one which is a whole bar, a normal whole bar, and the one which is a whole bar with a resonator that now is really a slot antenna, a rectangular one. And what we observed was there was this extremely large anisotropy, now we're talking about a factor of 50, between the resistance of the sample with the resonator as compared to the reference sample. And now we did a lot of checks, and what we see is that the sample without resonator has no anisotropy. So it's basically an isotropic phase, and the interpretation here is that we have still stripes, but they are oriented in all possible directions. So it's a completely degenerate system, so you don't see any anisotropy. And what we assume is now that the vacuum field fluctuation, and especially the gradients at the edge, tends to align the stripes and tend to align them along the cavity. Now, to support that idea, we actually also measured, you see here, we measured the longitudinal resistance by passing the current along the whole bar. If we pass the current across the whole bar, okay, we have a combination of bulk and also multi-terminal resistance, but still what we see is, of course, a complete inversion of the asymmetry. That means the sample with a resonator has now a much larger resistance than the reference sample. The reference sample has now a fairly symmetric behavior. And also, when we look at this asymmetry is temperature dependent and has not an activated behavior, but rather a power law behavior as a function of temperature. But the key message is you lose this asymmetry, anisotropy, when you reach something like a few hundred millikelvin. Okay. The explanation here, the theoretical model from Sam and Jonathan and in the group of Eugene Demler, is that what we have is we have this thermally disordered state, and that the cavity stabilizes it, and stabilizes it because we have basically an isotropic dielectric, which will try to minimize its energy, and it will minimize its energy when the stripes are aligned perpendicular to the electric field. And you have to remember that those cavities are very multimode, but a lot of the lowest order modes, they have the field which is perpendicular to the long side of the metal. So, as a conclusion, I just wanted to, because we're also in the context of theoretical physics, I just wanted to make a summary also of whatever we observed, what the models have been used, and what worked and what sort of worked less. So I think that historically, at least to us, the first model that was used initially by Cristiano Ciuti and then by Vasile Rocage is the Kubo formalism, where the idea was you basically introduce the strong coupling under the form of polaritons, showing that the transport is driven by the bright polaritons, and you need to introduce, one of the problems was you need to introduce a certain broadening. And that broadening for us never really matches what we could understand. And this, the hope was to explain the modification of Shubnikov, the Haas. Yes, it did a bit. It also predicted the normalization of the quantum Hall resistance, which for complicated reason didn't really observe, and a loss of quantization of the integer quantum Hall effect, more in terms of the temperature dependence of it. Now, the next step was this cavity-assisted hopping I mentioned. There you have a collective Rabi splitting, but it arises in the model not by postulating the existence of polariton. It arises naturally by summing over all states. So that is, this omega r is really a consequence of the model. You need disorder of field gradients. You apply Landauer, Büttiger for your transport, and there you sort of can predict the loss of quantization. And the last one is this cavity-assisted electron-electron interaction, which basically needs field gradient to the to explain the fractions. You need the magnetoroton. It nicely explains the normalization of the G factor, which is also the effect we believe now is responsible for the loss of quantization odd integer factor, and this better for fractional quantum Hall fractions. And with this, I also missed, of course, the stripes order, which is a bit of a separate thing. Okay, with that, I hope to show that hovering cavity in this quantum hole is a nice way to study vacuum field effect. We saw a number of important things, of nice things, and with that, I thank you for your attention, and thanks my group for the work.
Thank you very much. The talk is open for questions. I see one by a touch, just right behind you.
Thank you, Jerome. Very nice. So I missed the explanation about this with field gradients. You said that there is an effective long cavity-mediated interaction. So how does that help the fractional?
Because you change the Haldane potential. It's not enough to just say you have an attractive potential that will help the fractions. It is really, honestly, I don't know the details, but what I got from Cristiano is that let's say, the strength of the gap really depends on the relative strength of those Haldane potentials. And what you do is with this attractive potential, you change it. And you change it in a way that it improves, at least for the 1/3.
Yeah?
Yeah, Jerome, hi. Yeah, thanks for the fantastic talk. So the question regards this proposed stripe relevance in this system. So I didn't understand how much of this it's an explanation and how much of this is an hypothesis. And the question would be, can you think of structuring your antenna to test this hypothesis?
Look, what I didn't have time to show is we see the effect also a bit in the hovering cavity. So we see also a change in the Shubnikov-de-Haas, by far much less than what we observe when we have the cavity and directly on top. And what also is striking is the strength of this asymmetry depends. We had cavities that were made where we had a stitching error in the lithography, such that we had a jump of 0.5 micron or 0.2 micron. And that was enough to make the asymmetry between the two resistances much weaker. So, it's clear that in terms of really the theoretical model, that, I will leave maybe John answer. But let's say in terms of the physics, we are really convinced this is due to stripes.
Yes.
Hi, thank you for a very nice talk. I have a question about the model where you introduce vacuum vector potential in your Landau-level Hamiltonian. So is there like a spatial profile associated with that? Because there was no spatial dependence.
Right. So usually people would sort of assume as the electromagnetic field a constant field, and push everything through the dipole approximation. Now, what was new in Cristiano Ciuti's approach was that he explicitly put a field gradient. And therefore, but the field was, again, still, it's not it's a very rough approximation of what you have in the real sample.
Thank you.
Mohammed, yes.
Yeah.
So I misunderstood. Sorry.
Sure.
Now we can hear. So in both cases, for tunneling and for interaction, or even density-dependent tunneling, I think this beyond dipole approximation enters. So I think for his even original calculation, forget about the interaction, I think that comes into play. Or it was like ignored, or it was included but didn't have effect. So I missed the connection of this interaction. I think my intuition tells me actually the tunneling might be dominating everything.
Look, what you're referring to is I assume is that the cavity-assisted hopping term going up and down with not taking into account the disorder, but the field gradients.
That's right.
And we actually, your absolute intuition is right, because we basically have a student who made a little model where he introduced both. And it looks like having either doesn't give you a strong effect, but you really have a much stronger effect when you put both together. So if you induce disorder and field gradients, that's where he sees the strongest effect.
Yeah, so no, not invoking interaction at all.
No, this is just like the cavity-assisted hopping.
Hi. So you showed, again, a beautiful talk, but I'm wondering, you were showing how the fields are enhanced by screening, and it would seem you can change the amount of screening you have by the whole bar by changing the density of the 2D electron gas.
Right.
So does that give you a knob to?
Yes, yes, of course, absolutely. Changing the density of the 2D gas will change the screening. The problem is it changes a lot of other things at the same time, because for a given, the light matter coupling will change, will be lower for lower densities. And clearly, this is one parameter we need to investigate more. The samples and the experiment I showed you, the initial experiments and the one with hovering cavity are for a density of 210 to the 11. The effect of the stripes, we see it actually, we saw those also in the 210 to 11, but we saw them much strongly in the larger density samples, so 410 to the 11. And that's part of the reason. In that sample with larger density, we also saw a stronger renormalization of the G factor. Also maybe because the cavity was stronger. So, yeah.
Hi. So just to make sure I understand the model. So is the reason for the renormalization of this conductivity, is it due to the renormalization of the particles in the bulk, or is it some tunneling between the edge states?
You mean in which model now?
The first.
Right. So here the idea is really you have edge states, and what the model allows you to compute is scattering between edge states. So that's why I said typically this cavity-mediated hopping, the implementation was using, in addition, a Landauer-Büttiger approach, so that you basically implement this as a scattering mechanism between opposite edge states.
Still have a few minutes. One more question. Oh yeah, there's one. Andrew.
Thanks, that was a nice talk. So I was wondering, intuitively, can I understand why it was the odd states? I still don't think I quite get the explanation.
Okay, sorry, maybe I went too fast, but you see, the odd state, the gap between that creates the quantum hole in the odd states, is the gap between two Z-man splitted levels. And now the strength of that Z-man splitting, because we're now dealing with a quasi-static effect, is given by this Z-man energy plus the exchange, the contribution from exchange. Now, that's translated into this effective G factor. Now, if you change that G factor and you bring those two Z-man splitted levels closer to each other, then of course if you're doing too much, then you completely lose the gap. And that means you lose also your quantization. And that's why we understand now this very dramatic effect that we saw in the very first paper more as an effect of this collapse of the G factor rather than really the cavity-assisted hopping. Although, it's hard to sort of really distinguish the two. Because you see, the cavity-assisted hopping should not matter too much whether you're in a spin-splitted or a Landau gap.
Any final question? I think no? Okay, then let's thank. There's one more.
One like that.
Sorry, I was confused. Yes.
Sorry, maybe I missed this. How does the frequency of the cavity compare to the Landau level splitting?
Extremely good question. The frequency of the cavity, I forgot to tell it, is 140 gigahertz, which means that also all the main effects that I'm discussing are for magnetic field for which the cyclotron energy is actually quite larger than the frequency of the cavity. So this is a non-resonant effect. So the reason, now if you say, well, why don't you make a cavity which is much higher frequency? The problem is, yes, you can, but if you want to have very strong light matter coupling, then obviously you would need to make the whole bar very narrow. But now one thing also to keep in mind is that we always discuss this single mode approximation where we only consider the ground frequency of the cavity. Well, this cavity has many excited frequencies and they're all well confined because this is it's a metal. So you can think of that cavity having the ground frequency at this 0.6 0.6 Tesla, then the next excited state is going to be a 1.2 and so on and so forth. So there's really a lot of excited modes. Simply the light matter coupling will keep going down because the volume of the cavity compared to lambda is going to simply go down. So that's the effect. But in reality, of course, we should keep in mind this is an anti-resonant effect, and so you have to integrate over all the modes of the cavity.
Okay, one final short question.
Yeah, and I ask you to comment about the following. So the temperature is always assumed to be constant.
Mm-hmm.
How fair is that assumption given the fact that the gradients and the local aspects of the field are so relevant? Given also what we know about the radiative processes which affect the thermodynamics.
Let's see, what I can say is when the students forget to close the, let's say, there's always in the drill fridge, there are the plugs that you have to put in the various stages so that your radiation doesn't leak inside, you see it. So you see that your transport is now, you don't see the minima the same way, clearly. So what I meant is that, we are driving those samples with, nanoamps and millivolts, and so the input power into the sample is minimal. And, we see those effects, we see clearly, the very sensitive states, we see them going down all the way to 20 millikelvin. So my assumption is we are dealing with basically as close to thermal equilibrium as we can get. Of course, there's always a bit of deviation because you're never perfect, but honestly, to me, I don't see, my assumption is that everything is at the thermal equilibrium there.
Okay. Let's thank Jerome once more.
Thank you.